You can have the information. Okay, next Tuesday is the quiz lab, probably about 12:30. And remember, this is weighted more. Out of which 40 points is the spectroscopy part.
You said we're not going to have a lab final.
Yeah. Did we say that already? Is the surprise out? Yeah, we don't have a lab final. This is your final, okay, for lab, or it's worth as much as 2 quizzes, okay? Now the spectroscopy part, this will also cover whatever you get there will be counted as a lecture quiz or spectroscopy. Okay. So you'll still have to do the lab write-up, but nothing from that lab, or probably the theory part you'd have to know, which is also connected with lecture, okay? So the content or the labs that you need to review, that is on Canvas. So it's just that you look at it, and if I open it up here, I'll be able to show it to you. So this next week, with the lab final on Tuesday and the write-up on probably Thursday night or Friday, that'll end your lab portion. And then this Thursday, Becca, Michaela, and I will be looking at all your presentation scores. And sometime by this weekend, we'll be posting scores for that. Okay.
Did you say that you were going to have our quizzes uploaded today?
Yes.
Okay.
The one that you took, right? Yeah. Yes. And tomorrow is your lecture quiz, right? Let me update that as much as we know as of now. Tomorrow. And the sapling is posted for 19. And I would like to give exam 3 Wednesday of next week. And this will cover Wednesday or Friday. I don't want to push it because you have a lab final.
Yeah, I was gonna ask, would Friday be better because we have our lab quiz next Tuesday?
Yeah, so you have time to study. Okay.
Yeah, clear our brain of lab.
Yeah. Okay. And this will be CH18, CH19. This is new information. And I decided to go with this CH15, which is NR. And the few sections of, what was that chapter, Deanna? $16. So when you study, well, for tomorrow, that's review for exam 3. When you study for the quiz, the NMR part, that's review for NMR and 16 UV. Now for UV, I will be posting questions from the, you remember the Woodward? Okay, about the conjugation stuff.
Will we get a chart for that one?
Hmm?
Like the values for the
Yeah, yeah. It'll give the, I'll give you the values. We'll post practice problems. Okay. So exam 3, is everybody good with that? I think everybody's present but Carly. And I'll repeat this again tomorrow. So CH18, we've done everything over it. And my only concern is that you've not been tested over the mechanisms. So I might do like 25 points of the mechanisms from 19 on Wednesday. Do you understand what I'm saying? And is that okay?
What do you? Oh, like on the test?
Uh-huh. Like divide up the test into like 25 points, CH19 mechanisms, or 20 points, okay? And then give that on Wednesday, just that. And then the rest, 80 points on Friday. So you do only the mechanisms, read all that and take it on Wednesday. Does that sound like a good possibility?
Yeah.
So we are breaking it down, And then I'll know more about the week after, like the department, they're talking about what to do and things like that. So I'll know more by Friday and I'll do a post. Okay. If I know something tomorrow, I'll let you know.
Aren't they talking about making some classes pass fail?
That's not what the school is recommending. So they want we had a meeting yesterday and they said that that was not an option for us. So the school has to decide, and many large schools have gone that way, but I think we are not going that route.
Okay.
Yeah, I think somebody tried asking that. Some of us asked for a little bit more time because we are, behind on like grading and lab stuff, and lecture in general. So they let us know if they'll give us 2 or 3 days more of the semester. So we'll find out, but I'll keep you all posted. Okay. All right. Now let me show you what is in the if I can even go there. Give me a minute. I'll share my computer so you can see. If you go to Canvas and I put it up on top. So you have the IR table. I put up the big table so you can do a good analysis. Okay, so you have that. And then NMR tables. Where is it? Okay, so this is for the carbon-13 that we'll be using today. And then this is what I'm going to be talking about. Looks kind of strange, but it's not. And then the short IR table is given below. And then I have one for UV. And I have more information if you need it. Okay. Lots of information. Now, the only thing that, like I said, is that that template. So I'll be doing it this afternoon after we're done with class. And then there is also a table, and I thought I put it up, that has, let me see if it is on my computer. So I'm working on the template. See that? And then this is what I'll be posting. So you have to, I'll post charts for the solubility as well. So water solubility, is it soluble in water? So I have here discuss solubility. Are you able to see it? That's way too big, right? Okay. Discuss solubility in each of the solutions or solvents. So water is there, that's a solvent, both negative and positive. So if your chart says, if there's a dash there, that means it's negative. Let's say it's insoluble in water, then you'll say it's insoluble in water and some of these functional groups are not present. Okay, so you have to say a negative test means what? Absence of, you know, certain functional groups, if that information is given to you. Sodium hydroxide, insoluble. What does that mean? It's not a phenol, it's not this. All right, so you have to explain like that. Don't say sodium hydroxide solubility. Under that, just don't say, you know, negative. Well, you have to say negative. Shows the absence of phenol or something like that. Okay. I think it shows the presence of phenol. Shows the okay, but absence of something else. You know, if there's a test like that, absence of something else. Okay. Sodium bicarbonate's the same thing. It's a test for the presence of carboxylic acid. And let's, oh, it says negative show. I apologize for all of that. So sodium hydroxide, it shows negative. So you should say indicates the absence of phenol. I did write it correctly the first time, okay? You're supposed to have phenol, but your test is negative. So you just don't leave it as negative. You have to say what is that you're looking for under that test and what is not present. Do you all understand that part? Okay. So sodium hydroxide, let's say you thought it had carboxyl group, your structure, but you got a negative test. So you say indicates the absence of a carboxyl group.
Dr. Mary,
Mhm.
your screen is still on the modules tab, so we can't see anything you're talking
Yeah, I was
about.
very confused. What?
Thanks for telling me. And I've been just talking to myself. Okay. So this is the template that I've been preparing, okay? And it gives you like instructions and then breakdown of data, okay? Solubility data. I'll give you the solubility chart. It'll be a little bit more elaborate than the one that you have from your lab manual. So it says discuss solubility in each of the solutions or solvent. Both negative and positive results must be included. So for example, sodium hydroxide solubility usually indicates presence of a phenolic group. But if in your case it's negative, you just don't say, just leave it as negative. You would have to go and say, shows the absence of a group. Okay. That's what I want you to write. So you just don't look at the unknown assignment that was emailed to you. You have to look at the chart and say, what is it that it's indicating if it's negative? Because the negative results gives you a lot of information as well. And then the next one, I did this example. Let's say you got a negative test for this. Carboxyl, absence of carboxylic acid or carboxyl group. Okay, so that's how I want you to discuss. The same with the functional group analysis. Tollens test, you don't get the negative, you don't get the silver mirror, negative absence of an aldehyde. See that? That's how I want you to go down the list. Now, iodoform tests, those are some of the tests that I will include because we did not do that, I think, in, I know we didn't do it, but I don't know if it's recorded in your lab manual. And Lucas test, Hinsberg, this is a test for amines. So if it's negative, then you will say absence of an amino group.
And if it doesn't say anything, should we just say test not performed?
No, if it doesn't say anything, I saw that, that means it's negative. Do you see a nitrogen in your formula? If you don't see a nitrogen, then can you have an amine?
No.
So it
So
means,
if it doesn't say anything, it's just negative.
Yeah. Okay. If it is positive, then it'll tell you what the test is about, okay? So then I have mass spec data, and then I'll show you that I'll say analyze the fragments or something like that, or draw the spectrum or something like that. Unsaturation, HDI, NMR, I've broken it down just like you did the NMR report. Fragment, complete structure. Oh, I shouldn't say complete structure here, okay? I'll take that out because you will do it after you do the UV. And some of you on the UV, it says transparent. That means you do not have any of the pi to pi star transitions, any of the N to pi star, so it doesn't have a pi bond or lone pair. I don't know about lone pairs. You may have lone pairs, but there are no pi bonds. Okay. So this will go in conjugation with the HDI information as well. IR, we did this by the IR lab. So I put that table up. And then finally, you'll do the structure and the name. You can always Google, we know how to do that if it's not in your textbook. Got that? Okay. So this is what I need to, fill in some information. So I'll put the solubility data and the functional group analysis. I consolidated everything for the functional group analysis. It took me a while because it was always easier to do in the classroom. So Becca helped me reformat this as well. So I'll have that available this afternoon. Okay. So all your tables are there. And then I will also include the functional group, tests here, the solubility data, and the template will go here. All right, so this is where it's found in the lab canvas. Got it? Okay. Any questions? Okay, so we'll at the end we'll come back, and if there's anything that needs to be said, Michaela just came in, we'll do that at the end. I think KJ. Oh, by the way, did y'all put up your papers up here on this link and the PowerPoint? So this week is when we'll be looking at it. So you need to upload whatever has not been uploaded for that. All right. And announcements. This was what Becca had mentioned. So like I said, the esterification lab is the one that you will do next week. Lab quiz, and these are the things that you'd have to review, okay? Only theory for these three synthesis labs, because we didn't do an experiment. But the theory is all linked with lecture, all right? So, okay. Before Ken goes to sleep. Okay. All right, Ken, you want to?
Oh yeah, I'm ready.
Okay. You want to take over the screen?
Mm-hmm.
Okay.
Let's see. All right, so basically I'm just gonna be going over what I went over last week.
Mm-hmm.
Carbon 13 NMR.
Mm-hmm.
Let's just go. Okay. So we learned that H1 NMR has three characteristics: chemical shift, integration, and multiplicity. But carbon 13 only has one characteristic that we look at, and that's going to be the chemical shift. So as you can see, all the signals are recorded as singlets, and splitting is not observed due to a low abundance of carbon 13 atoms. The reason why it's low abundance because only like 1% is seen in each carbon.
Can you do the slideshow, please, if you don't mind?
Oh yeah, my fault.
No, that's okay.
Because I can't see my my mouse or cursor. Because
We can see it.
oh, you can. Okay.
There you go.
All right.
All right.
Let's see. Okay, hold on. I can't see my mouse.
Sorry.
It's okay. Hold on. All right. Okay.
Play.
There we go. All right. So we say carbon 13 splitting isn't observed, but carbon 13 and hydrogen splitting can be observed. And the splitting causes signals to overlap and produce unreadable spectrum due to complex splitting patterns. And this problem can be solved through broadband decoupling. So broadband decoupling uses two RF transmitters. The first one gives short bursts in a range of frequencies that causes the nuclei of carbon-13 to resonate. And then the second one continuously irradiates the sample with a span of frequencies that cause the H1 to resonate. And then the second RF source also decouples the two elements and causes the signals to collapse into singlets that we see here. Okay. And so we learned about off-resonance decoupling as well, because as we can see, broadband decoupling doesn't show us everything. So off-resonance decoupling helps us discover the multiplicity in all the in the spectrum and like and the other stuff that we can't see in broadband decoupling. So as we can see here, off-resonance, we can see triplets, and we can see quartets in off-resonance, but broadband we only see singlets. And it's a reason why we do both. The reason why we do broadband is because it's simpler. You can see everything clearly. And the reason why we wouldn't want to do off-resonance is because it's complex and it's like kind of hard to read each spectrum. But this one is kind of clear, so. All right. And now we go over the chemical shifts in carbon-13. So the chemical shifts operate on a different frequency compared to H1 NMR. And we can see that the values range from 0 ppm to 220 ppm. If we go see this, it's the unique carbons. Each unique carbon is highlighted in the example here. So as you can see, it's like you can see the 4 signals, 3 signals, and 5 signals. The unique carbons are ones that cannot be interchanged by symmetry. So this is an example in there. Okay. Let's see. All right, the location of each signal is dependent on the shielding and deshielding effects, just like H1 NMR. So you can see here, methyl groups like sp3 hybridized carbons are going to be 0 ppm to 50. sp hybridized carbons and sp3 hybridized carbons are going to be 50 to 100 ppm. 100 to 150 ppm is going to be the sp2 hybridized carbons, and any carbon with the carbonyl group is going to be 150 to 220 ppm. All right, so we did a little small sample problem here. As you can see, there are going to be 5 unique carbons here, because if you split it down the middle, you can see the ones that can be interchanged by symmetry. So let's see. This problem you can see is 2 methyl groups, and they're usually equivalent. However, in this instance, they can't be equivalent because one methyl group is going to be cis to the carbonyl group, and the other one's going to be trans to the carbonyl group. So it's going to be 2 different signals to be created. The chemical shifts here are seen here in this problem. You can see that the 2 methyl groups are going to be 0 to 50 ppm, but they're going to be different ranges because see, one is cis and one is trans. The 2 sp2 groups are going to be 100 to 150 ppm, and carbonyl group is going to be 220 to 150 ppm. I had another problem. Hold on, let me show you guys. Just a second. I'll put it up here just a second. All right. Let's see. All right, can you guys see that? All right, so I made this like 2 seconds. So, and as you can see, I just highlighted all the unique carbons here that are not interchangeable by symmetry. So I split this down the middle. I get 4 unique carbons, and I place them on my graphs here. So you can see the methyl group here It's going to be between 0 and 50 ppm, and all three of these are going to be SP2 groups. So the SP2 groups are going to be placed between 100 and 150 ppm. Are there any questions? I kind of went through that kind of fast. Sorry about that, but you know, it's kind of simple once you get used to it. But that's all I have to say.
I have a question, but like before I do, like I just want to make sure that like somebody who needs to ask a question should go before me if they have one.
Okay.
Anybody? No?
You're all good.
All right. So you talked about like system trans configurations.
Yeah.
Is there also like situations where E and Z configurations will matter?
Hold on, let me go back just a second. Oh gosh, let me see. All right, go back. There you go. All right, you said E and Z.
Yes.
Yes.
Because I guess like in this one, if they were what is like E, you know, like that definitely affect it, but
Right.
yeah.
Yeah, I think so. You know, I'm agreeing with the KJ in that. If you have a double bond, sorry, I'm trying to eat something. Whether it's cis or trans or E or Z, I think it'll be affected.
Mm-hmm.
But if it is sp3, then there's rotation, and so you will not see a change like in the case of a double bond with different groups on different sides.
All right.
Can you go back to the ones that were showing the symmetry, please?
Sure. There we go. Oh, hold on. This right here?
Yeah.
Okay.
So in the example that you did was equal to the one on the bottom.
Oh yeah, okay. Yeah, I see what you did there. Okay, yeah. All right, so all right, hold on. So let me go back to my example. Let me see. Hold on. All right. Okay. So my example, I said there was 4 unique carbons, but in reality, it's supposed to be cut in half between here too, because these are symmetric. So it's actually supposed to be 3 unique carbons instead. So it's supposed to be 2 sp2 groups instead right here, and it's supposed to be 1 methyl group right here. So just don't mind this one or this right here. So my bad about that. I slipped up. My bad.
What's the question there?
Hold on. Let me show you.
Is this the para?
Yeah. Let me see.
Play there. Right there. Yeah, go. Play. There.
All right. So as you can see on this example, it's like 3 signals. But on my example, I put 4 signals. So it's supposed to be split in between 2 because they're symmetric on the bottom too. So I didn't see that.
Yeah, yeah. Did you draw 4 signals?
Yeah, I did on accident.
Okay, all right. Yeah, it should be 3. That's the most symmetrical.
Right.
Of them all. Okay.
All right. Are there any other questions? Oh.
Okay, all right. Thank you, KJ, for repeating.
Uh-huh.
reviewing, I should say.
Let's see if I can find it.
All right, now I have mine as a PowerPoint. This is in your PowerPoint that's on Canvas. Now, what KJ talked about was the basic carbon-13 NMR spectra. And like we said, that the complex splitting is removed and we have just singlets for all the carbon atoms present. So it's broadband decoupling. Okay, that's what we call the type of C13 that KJ just talked about. Now, this type that we're going to talk about today is called DEPT, distortionless enhancement by polarization transfer. Okay, so we're not going into the instrumentation for this, but we are going to look at the results. Again, you're going to get single peaks for each carbon, but we are going to look at the shape of the peak and the orientation of the peak. Now, this will also tell you information about how many hydrogens are attached to each carbon. Isn't that lovely? So the full decoupled, okay, the broadband decoupled is what we call the spectra that we've seen so far. Okay, broadband decoupled. You should know the terms because you would be asked to distinguish between the different kinds. And then the DEPT, okay, the distortionless. I even forget what that E stands for. Enhancement by polarization transfer. Okay, we just go by DEPT 90. So there are two different types. One is 90 and one is 135, depends on angles and things like that. That's used in the instrumentation. So the 90 shows only CH signals. Isn't that nice? It shows only CH signals. And then the DEPT 135 shows signals for both the methyl and the methine. Remember, we talked about methyl and methine. And they're positive signals. What does that mean? They will all be pointed up, like the electrons. Like when you draw them, you draw some up and some down. But if you have a methylene, those are singlets, but they point down. All right, so you have to remember this. Which one shows what, and the DEPT shows them all, and how are they pointed? So this is a broadband decoupled. It's just all up, okay? Singlets going up. DEPT 90, it only can receive information from the CH or about the CH, so only those are shown and it's pointing up. DEPT 135 shows signals for all of them except the carbon. It's called the quaternary carbon, which the carbon is attached to other carbons or other groups, okay, the quaternary. So that information about that is only given in the broadband. So look at 135. This guy goes upside down. It's like, okay. It may have to depend on how many hydrogens there are and so on and so forth. So CH, if it's present, if you see a peak present in all three, then you know that's a CH. If you have a peak present up like that, standing up in 135 and in the broadband, but absent in the DEPT, then it's the CH3. If you see this guy anywhere standing upside down, that's a CH2. See that? Okay. So you have to, this chart will be given to you so you don't have to remember, but it shouldn't be given to you, right? But I'll give it to you this time so you would know which is which, okay? So there's so many other techniques that are used to pinpoint more details, but this is what we are going to learn from this chapter. All right, so we have 2 extras and they usually analyze all of them at the same time, okay? And let's look at, let me have to do another share. Are you able to see, are you seeing the same thing? I have to do a new share every time. Now I'm going to look at an example in the textbook. Okay, so this is how it'll look like. I don't know how to make this bigger. Now look at the broadband decoupled. Can you tell me what these are? Look at this, 0 to 50 and 50 to 100. What kind of, I don't have the KJ. What do you have between 0 and 50 and 50 and 100? Anybody with a table?
Let me see.
Those are the
Methyl,
SP3, right?
yeah, methyl groups.
0 to 50. I have the book. Let me open it. Okay, 0 to 50, mostly those are the ones that we were talking about. Okay, now it goes a little bit over, but they're still sp3. It could be a, you know, we would have assumed that that's possibly a CO, but doesn't look like it. Okay, now look at, so we have 3 of these. And this has gone slightly over the range that's given in your chart, but it's still an sp3 hybridized carbon, okay? So sometimes they can go over. What is this peak that's still standing up in DPT 90? What is that one? Adele, what's that one? At 30?
Is it the CH group?
Is it the CH group that is flipped? No, it's not flipped, but that's the only one that's in DEPT 90. So this is the CH group, and that's also standing up and it's present in DEPT 135. What is this one that's not present in DEPT 90, but it's upside down in 135?
CH2.
CH2. And what's the last one? Oh, the first one on this side. that's not present in 90 and it's positive in 135, that's the CH, what signal?
Methyl.
Methyl. Everybody with me? Okay. Let's do one more. Let's see if we can do this time. 90 is not given. It says 90 has no signals. Okay, it says 90 has no signals. Can you do a quick analysis? I'll give you a minute. And everybody understand it because it's not too difficult. And then can we determine, first give me the analysis.
Shelby sent a message.
Somebody sent a message?
Shelby did.
No, okay.
Dr. Mary, I can't see your screen. I can just see your video of you.
Oh, really? Oh. Oh my gosh. Okay. Are you able to see me now, Shelby? I'm doing a new share.
Yeah, I can see you.
Oh, I see. You're not able to see the screen?
No, it's just your video of yourself on the big portion.
Okay, so the others are able to see it, I think, right? Okay, so can you go hover over to the right possibly and see if you can?
Gracias. ¿Qué es?
Hey, Shelby.
Oh, sorry. I think her screen froze. Do that and the next one too. And for 1528, I need a structure for the compound. Are you still able to see it? Yeah.
I got mine.
Okay. All right, great.
Dr. Mary, I can't hear what you're saying.
You're muted.
Okay. And there's a chat. Oh, you're muted. Thank you. Okay.
I was wondering why it got so quiet.
Yeah, and I was speaking and nobody was saying anything, and so I was wondering what happened. All right. So, how many on the broadband decoupled? How many peaks do you see? Broadband decoupled. How many peaks? 5. How about John? What do you see?
5.
5. There's a teeny weeny one
I think
here.
I see 6.
6.
Oh wait, no,
Where?
I was looking at the bottom one.
No. Okay.
I was looking at the bottom one.
So, the bottom one has, oh, you're looking at the, oh, I see, the next problem. Okay, so this one is 5. These are the ones that show up on the 135. So these are, again, it's in the region 0 to 50. And so these are your sp3 hybridized carbons. So let's go through our list. Do you have any CH peaks? CH? No, because DPT90 is 0. No signals. If you read the problem up on top, I'm able to read it. DPT90 spectrum has no signals. What about CH2? How many CH2s do you have?
2.
2. How many CH3s?
2.
2. How many quaternary carbons? Quaternary carbons. What do you mean by quaternary carbons?
Like a CH, right?
Quaternary, no.
Oh.
Carbon attached to 4 other carbons. Do you have any? No. Look at the broadband. Look at this figure. It's so hard to go back and forth. You see this here? This is the quaternary carbon. And it doesn't show up at all in these 2. So that's the quaternary carbon. You don't have any. Now, so you have 2 CH3s, 2 CH2s, and what is this guy over here? This teeny weeny between 200 and 250 or whatever?
Carbonyl group.
Carbonyl. Okay. So what is the structure then? Can you all draw the structure? Got the structure? Ken, do you have a structure? I've got to go in a minute.
Yes, ma'am.
What is it?
Trying to see how to say it.
Well, you should know how to name it, right?
3-penta.
3-pentanone.
Yeah, pentanone. There it is.
3-pentanone is the structure. Okay. I have to go give a quiz to someone else. I want you to work on, I'd like you to work on 29 and 30. And I'm just going to be away for a couple of minutes. I can see still everything that's going on. And can you all do 29 and 30, please? Becca, can you help them for 5 minutes?
Yeah, I'll do what I can.
Yeah. Okay, I'm back. C5H12O. There's one at 73.8. So that oxygen, what do you think of that oxygen? Sorry, meddling with this. Hutch, when you're done with 29, I'd like you to discuss your answer. Becca, you're able to hear me, right?
Yep.
Okay. Hutch, are you there?
I'm here. I'm just still trying to figure it out.
Okay, okay. Thank you. Take your time. Just because I'm not seeing all of you.
Okay, I think I have it. It would be, let's see, 3 pentanol. Yeah. Would it?
That's what I got.
Sorry, I thought I was on. Um, okay. DPD 90, 73.8. That's a CH, isn't it? Right, Hutch?
Yes.
Okay. What about the one, the negative one? That's the CH2?
Yes. I
Okay.
had a CH, a CH2, and a CH3.
Okay. And then what is the structure you said?
3 pentanone. Oh, not pentanone. Pentanol.
Pentanol? Yeah. Yep. Did everybody else get that?
No, how did we come to that conclusion? I'm lost.
Okay. So I'm gonna hope you have that information. I think we are missing a, okay, let's look at it. Okay, new share. Okay, what are all the pieces we have? This is the broadband decoupled. And the DPD 90. $73.8. DPD 135. Then I have a positive at 9.5, and then a negative. All right. Okay. Is there a quaternary carbon? I don't know why I drew it so big. Okay, I'm just drawing all the pieces that I need. Let's go down the list. Do I have a quaternary carbon? No. Do I have a CH? A CH, this is a CH. It's the only one that's available in the 90. So there is a CH. And then is there, what's the one, the guy that's upside down? He's the CH2. This guy, CH3. So we have, everybody agree that we have a CH, CH2, and a CH3. That's what Hutch said. Everybody okay? Everybody still listening?
Mm-hmm.
Yep.
Now, okay, good. Now, just I can't see your faces, so I don't know. C5H12, right? Oh. Now there's no carbonyl group, there's no CO single bond. So it must be an OH. Okay, must be an OH. Now we have 5 of these. So we have a CH2. They did not tell us how many. Yeah, Shelby, is that you?
Yeah, I have like 7 minutes to get to work, so I gotta go.
Yeah, that's fine. That's fine.
Okay.
Yeah, I said only till 1:30 we started doing the problem, but you're okay to leave.
Okay.
Okay, I'm still recording, okay? Okay. And then a CH3. And then a CH3. Where's the CH coming from? They did not tell us how many of the CH2s you have. All right. Is there another way to put it all together? Because they did not tell us how many CH2s there are. Could he have done? He did it because he thinks these two will overlap, and that's a good possibility because they are symmetrical. See that? So this CH2 will overlap with that CH2, so technically you'll get one signal. Okay. One last one. Can you try the next one? You want the screen back? This one here. And there's a little teeny weeny thing here. Okay. Okay. Deanna, you want to try this one? I'm going to do the document camera now. Okay, let's draw a diagram. Okay. And everything here is within 50. Up, 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 and up. 1, 2, 3, 4, 5. And let's see, a teeny weeny one here after 200. 90. I don't know which one I can't see. One of these middle ones is up. Okay. And then 2 of these are down. And then 3 of these are up. Okay. Any quaternary? No. And then CH, H2, H3. Okay. What is this guy? DPT90. What is that? Is that Adele? Adele, what are you doing?
Yeah. So,
Are you playing a video?
no, I think there's like an ambulance running down my street.
Oh, okay. Is that a CH2? And if so, how many? Deanna? She left us.
Is there 2 CH2s?
Sorry. Yeah, there are 2 CH2s. Very good. How many CH3s?
2.
And is that a carbonyl, the one here? Teeny weeny? Now, there's only one oxygen, so it cannot be an acid or an ester. It's either an aldehyde or a ketone. It's not an aldehyde because there are CH3 groups, so it's not terminal. You see? You have to look at all the information. And there are 7 carbons. So how will you place this? How will you do it? Or you know, maybe I'm wrong about the CH3. You could have an aldehyde because you can have an isopropyl group. So what's the structure? Any thoughts?
I got a ketone.
Okay. You know, unless we have more carbon, I mean NMR, proton NMR data, I think we can have more than one structure. You have a ketone. What's the name of the ketone, Ken?
4-heptanone.
4-heptanone. Where's your CH then?
Oh, okay. I probably got that wrong.
Mhm.
I did,
Did you do like this? Isopropyl?
Uh,
We cannot do isopropyl.
well, because then there would be 7 signals, because one of those.
Yeah, and then we need a terminal here. So I think how about an aldehyde? I don't know.
I did,
Mm.
I don't know.
Okay, so they've given you more information. If this is the problem that you're looking at, let me pull it up. They've given you proton NMR. Look on the bottom, there's proton NMR information. The proton NMR gives 5 signals. One of the signals is a singlet at 1.9 with an integration of 3, and another is a doublet at 0.9, integration of 3. I mean, integration of 6. So if you have a 6, what does that tell you?
¿Quieres más? Dame un poco.
¿Ya no quieres otro? Como más o menos.
Two, three, 4, 5, 6. I think there should be another CH3 group that's similar. You see that? That's where I think we're missing. There are a total of 3 CH3 groups. Why do I say that? Go add up all the carbons. Go to this one. 1, 2, 3, 4, 5, 6. But this formula tells you that it's C7H14. Oh, okay. So if you have an isopropyl group, then you can have 3 methyl groups. All right. And then let's look at the NMR together. I know some of you have other things to do. What's the NMR saying? The NMR is saying integration of 3, 1.9 ppm. It's a singlet. Another is a doublet. Okay. Another is a doublet. So they're giving you only, there are 5 signals, but they're giving you only 2 of them. Okay. Doublet. NMR, total 5 signals. Only 2 shown. And this is 3, and this is 6. All of them are CH3 groups, so that confirms that there are 3 CH3 groups. Okay, and this one, like that. Okay, could be an isopropyl. And the other one is a singlet, so it's isolated. And this is a doublet. So what is this group? This is a doublet. So what is this group? It's an isopropyl group. Okay, it's an isopropyl group. So you have an isopropyl group, and this is an isolated methyl group. Now, can you piece it all together? I think you'll get the answer. And tell me the name of the compound. Does it make sense? Okay. What's the name? So this is 3 carbons, that's 4th carbon. Okay, isopropyl. Then this methyl, it's not split. You see that? This end terminal methyl is not split. So this must be the one next to the carbonyl group, because there's no quaternary carbon. So 1, 2, 3, 4, 5, 6, 7. Now go back and look at the broadband. And these two, they gave you one signal. Makes a lot of sense. 1, 2, 3, 4, 5. And this is the one after 200. Okay. So on the test, you'd maybe asked, and even for your own compound, I could ask you to draw the carbon-13 NMR. You know, crude diagrams. All right. Does that make a little bit more sense? I'm going to say yes. All right. There's a chat here. Oh, okay. Oh, sorry to hear that, Deanna. Yeah, if you need to go, that's fine. Oh, that's so hard. Okay. Okay. All right. So all right. I don't know if Michaela had any. It's Courtney's birthday today, guys, our TAs. And so if you want to send her a text or an email wishing her all through Canvas, I think she would appreciate it. So I'll see you tomorrow at 12 for our quiz, lecture quiz, and be studying. Hope you did well on the packet. So she's grading all of that. And I don't know if there's anything else. Any other questions? Stop.